If I started too soon, it doesn't record. Okay, perfect. So we are discussing 11, and this is on page 203. And 11 is P equals 75,000, R equals 4.5%, and T equals 3 years. Okay, careful. If I'm asked to use 18 months, that will be a year and a half. And if I'm asked to use 9 months, I have to change 9 months into years. Okay, be careful. T is in years in this formula. Okay, perfect. So first of all, the compound interest continuously is the accumulated value equals the principal e to RT. So then A equals, the principal is 75,000 multiplied by E. R has to be changed into a decimal number, 0.045. And the number of years is 3. That's all we need to do. We have to plug it in. No one can calculate this. So we have to put it in the graphing calculator. And okay, so we have 75,000. And then E, where's my E? Okay. And you know my preference of parentheses. Some calculators don't need it. This one doesn't, but I'm just used to it. Okay, so enter. So we get the accumulated value is 85,840 plus 0.26 and 26 cents. So if the interest is compounded continuously on $75,000 and the interest rate is 0.45 for duration of 3 years, we get a difference of about $10,000. Okay. Now, part E, I believe. Again, find the doubling time. So I have $75,000 and I want to know how long it takes for it to double. What does that double mean? To 150,000. So it's 75,000. So doubling time. They want to call it in this book uppercase T. Fine. So A is 150,000. 75,000 equals E to 0.045 times uppercase T. So at this interest rate, they want us to determine how many years are needed for this investment to double. Okay, this is what we call an exponential equation. How do I solve an exponential equation? Does anyone remember the steps? What should I do first? Anyone, please. What should we do first? So we're solving for T. Please help. Jordan, what do you think? Jordan doesn't want to talk to us. Matthew, what do you think? Okay, Matthew doesn't want to talk to us. Oscar, what do you think? It's okay. It's okay if you are wrong. I just want to think, just to see what you think. What would be the first step? It's okay if you're wrong. But just looking at this equation, assuming, let's say, you know nothing about exponential equations. I'm starting everything from scratch. I'm reviewing everything. But what would be your first thought? What would you do? It's okay if you're wrong.
Yeah, I'm not sure.
It's okay. Devin, what do you think? I just want to see at least who is here and who is not. Devin, are you with us? Okay, so I'll have to make sure that attendance is accurate moving forward. Yes, Matt, go ahead.
Would it be 75,000, and then you square it by 0.45, and then just do it over and over again, and like use the caret sign in the graphing calculator?
This is way more simpler than that. So all I wanted my students to say right now is clean it up. And I would have cleaned it up. I would have divided both sides by 75,000. That's all I wanted to hear. Even if we know nothing about the exponential equation, I was hoping that somebody will say, hey, just divide both sides by 75,000. Make it as easy as possible. That's all I wanted. Okay, does anyone remember how we continue? How do we take it from here? Okay, so in this situation, in order to solve this equation, we have to apply the inverse function. So obviously this problem should have not been into that one because we haven't talked about the inverse function yet. But we have to solve it now because we started it. But we haven't talked about the logarithmic function yet. So it's okay. I'll come back to it when we get to logs. But since we started the problem, we have to finish it. So the inverse function, and let me share my screen again for a second. See, in the graphing calculator, on the same key, we have 10 to the x and something called log, which is basically the inverse function of 10 to the x. And it has base 10. We do not write base 10. This is my next step where I'm gonna show this, but it is what it is. I mean, it shouldn't be at the beginning of the section. It should be towards the end, this question, but it's okay. Okay, so the same thing you see on the next key. In blue, activated with second key, and in white on this black key, these two are inverses of each other. And they both have the same base. These two have the same base, which is 10. These two have the same base, which is e. Because the base on this side is e, I will apply natural log to both sides. And why is that? Because one of the properties of the log, and I'm going to list them here, properties of logarithmic functions. Are the following. First property, log in any base of a multiplied by b is the sum of the logs. Log in base a of a, log in base a of b. So if I have a product, this is not the case. I'm going to get to the third property in a moment. When we apply the log function, which is the inverse of exponential, I'll explain and we'll graph them in a minute. When we apply log to a product, this can be broken into a sum of two logs. The same thing when we have a quotient, a ratio. So number 2, log of a over b in any base. This is the same, but it's the difference. Same idea. Log base a of a from the numerator minus log base a of b. And now I'm coming to the property that I need. So property number 3. log base a of x, let's say, to power b. This number goes in front as a factor, not a term. It means it multiplies this. A factor multiplied by log base a of x. So this is the product rule. This is the quotient rule. And of course, this is the power rule. So product, quotient, power. So these are the log properties in any base. So coming back to my example, I'm going to copy it here again. So that was natural log equals natural log of e raised to 0.045 t. So there is a power. I'm applying the third property by bringing b in front, but this time is this. So I have natural log 2 equals 0.045 t multiplied by natural log e. Well, this is another property. Log in base a of a, this is always 1. Same thing here. When you see natural log, you don't see the base. Yes, you don't. Because by convention, we know it's e. We don't write it. So log base e of e is also 1. So this piece is 1. So that's another property of logs. Log base 10 of 10 is 1. Log base 5 of 5 is 1. Log base 1/2, log base 1/2 of 1/2 is 1. And so on and so forth. So now I'm finally in the position of determining t. This over this. So natural log 2 over 0.045. And now we'll approximate the number of years with a calculator, of course. So let's do that. So I have natural log 2, close the parentheses, divide by 0.045. And for the investment, the initial investment of 75,000 to double, we need 15 and 0.4 years, roughly. So a little bit more than 15 in order to see this investment doubling. So this was an example on continuously compound interest. And this was an example, the second half, the doubling time. This was an example on how to solve an exponential equation. And it was necessary to apply the inverse function. Why? Because of this property of the log. Only that property allows me to remove this power and put it in front of natural log e as a factor. It turns out that this is 1, and then I divide both sides by 0.045 to determine the number of years needed for the investment to double. Okay, now I would like to finally talk about log, which I didn't. I just used what we needed. We were supposed to go through the properties anyway. But I would like to talk about log before we go on. So logarithmic function not friendly. It joins the list of rational and radical with an even index. So this is not friendly, this is not friendly, this is not friendly. If you remember what I called not friendly, it means it's not defined on all real numbers. And of course, because we have two shapes, I need to go back, okay, here. Because we have two shapes, for the exponential function, we will have two shapes for the logarithmic function. One for the base greater than 1, and a different one for the base less than 1, between 0 and 1. The properties of the base are the same. So if the base is 2, log will have base 2 for the inverse function. If the base is e, the inverse function will be natural log. If the base is 10, the inverse function will be common log. If the base is 1/2, the base of the log will be 1/2 for the inverse functions property to be applied. Okay. So this was my page 2. And 3, 4. Okay, now I'm in order. So let's look at the two examples. Exactly what we just had. So f of x equals log base 2 of x, which is the inverse of exponential function inverse of 2 to the x, and log base 1/2, so this is f of x, log base 1/2 of x, which of course is the inverse of 1/2 to the x. Okay? So I'm going to graph both. So you can see them together on the same coordinate system. Which functions? These two. Which functions? These two. So you can see them. I'm going to graph one as a dotted graph. So 2 to the x, I'm just going to graph it dotted, because this is not what we are interested in, but I want both on the same coordinate system. So this is 2 to the x. How will I graph the inverse function? Every time I graph an inverse function, I draw this line that is y equals x, which bisects the first and the third quadrants. What do I do next? I reverse the graph, meaning I graph a mirror image of this graph with respect to this line. Okay, how does it look like? This is the graph of log base 2 of x. As you see, this one is increasing, so is this one. This one has 0, 1. This one has 1, 0. So log in any base of 1 is 0. That's another property of the log. Now, I would like us to determine the domain and range. Can anyone give us the domain and range for the log base 2 of x? Look at the graph, and then we're going to look at limits, so we can establish that too.
Is the domain 0 to infinity?
Excellent. Don't say anything. 1 second, 1 second. The range of the exponential function has to be the domain of the log function. That's how inverses work. So if the range is 0 to infinity, the domain of this function has to be 0 to infinity. And what about the range?
So then would the range be negative infinity to positive infinity?
Absolutely. Thank you. Absolutely. They have to be reversed. That's why I say that the log is not friendly. The exponential is. It has domain this and range this. In order to bring everything back with an inverse process, of course the domain of the log is this and the range is this. Same thing for both of them. It doesn't matter. Good. Okay, so let's graph the other shape. So if you remember, we had this. So this was 1/2 to the x power. I cannot graph the inverse function before I graph the bisecting line. Y equals x. And now I'm ready to graph, and be very careful. This function crosses here. The other one has to cross there as well. There is no cross here. 2 to the x does not cross y equals x. So, of course, this one cannot. But if a function crosses y equals x, when you reverse the points, you still get the same thing. So it's part of the other graph for sure. So this is log base 1/2 of x. Domain and range the same. Domain 0 to infinity, range all real numbers. Okay. Of course, this one passes through 0, 1. This has to pass through 1, 0. No discussion there. Notice that both functions are decreasing. When the base is greater than 1, both functions are increasing. When the base is less than 1, of course, both functions are decreasing. Okay, so finally, I just want to talk about the limits. So limit as x approaches, of course, 0 from the right for the first one. And limit as x approaches infinity from log base 2 of x, from log base 2 of x, and the other one on the other side, limit as x approaches 0 from the right, from log base 1/2 of x, and limit equals, and limit as x approaches infinity from log base 1/2 of x. So let me make sure you can see the graphs. For the first one, can anyone give us the limit as x approaches 0 from the right of log base 2 of x?
0.
Let's look at this carefully. As x approaches 0 from the right, the function values get closer and closer, closer and closer, closer and closer. We read from the y-axis because we are talking about the tendency. What will that be?
Negative infinity.
Perfect. Good. And limit of log base 2 of x as x approaches infinity.
0.
Okay, let's take a look. As x approaches infinity, the function values get closer and closer, closer and closer, closer and closer, closer and closer, closer and closer.
Is it positive infinity?
Perfect. On the other side, as x approaches 0 from the right, function values go to as x approaches 0 from the right, function values go to
Infinity.
very good. As x approaches infinity, function
Negative infinity.
very good. Perfect. Thank you so much. Yes, the functions, both of them, have x equals 0 vertical asymptotes. X equals 0 vertical asymptote. There are no horizontal asymptotes here. Okay, so now we're ready to look at anything else and also solve equations. The floor is yours. We choose. Now, use a calculator to find each log. I don't think there is a problem. I think we looked at an example a minute ago. We can plug it in and put parentheses and just determine log. Okay, let's take a look. We are given here natural log 4, as if we cannot determine it ourselves, and natural log 5, okay. Use properties of natural logs to find each value. Do not use a calculator. Okay, so let's look at and let's choose anything from 27 to 38.